I'm Sabrina Octaviani from Metallurgy and Materials Engineering, and I'm going to present about video assignment in week 2. First, explain how thermal transition influence the mechanical property of polymer. First we can look at the glass transition temperature. If we look at the picture, I will explain it. So, below transition glass temperature or glass state, the polymer in a glass state is a rigid state. The molecular chain are essentially frozen and exhibit very little movement. This results in high stiffness and strength with very low ductility. The material behave in brittle manner and can fracture under stress without significant plastic deformation. At TG, the polymers start to transition from a glassy to rubbery state. The phase change are the gradual softening as the chain begin to have decreasing mobility. There is marked decrease in stiffness and slight decrease in strength. While ductility start to increase, the material become less brittle and more capable to deform plasticity. So in above TG or rubbery state, the chain significantly moving, but they are not completely free flowing, characterized by low modulus elasticity, low stiffness, and moderate strength. The ductility of the polymer increased significantly in this state, allowing the material to be stretched and deformed. And the melting temperature below TM or semicrystalline state, the material exhibit a combination of crystalline and amorphous region. The crystallized regions contribute the higher stiffness and strength, while the amorphous region provides some ductility. As the temperature approach TM, the crystalline region start to melt, leading to decrease in stiffness and strength. And at the TM, at the melting temperature, the crystalline region of the polymer melt, and this result in significant reduction in the polymer stiffness and strength. As the material loses its rigid crystalline structure, the material can flow and deform easily, showing high ductility in this molten stage. And at above TM, beyond the melting temperature, the polymer in fully molten state, the mechanical property are not applicable in the conventional sense, as the material behave in viscous liquid rather than a solid. The comparison of thermoplastic, elastomer, and thermoset. First, for elastomer, for structural feature, thermoplastic consists of linear or branch polymer chain without any significant cross-linking, and the structure allow chain to slide past one another when heated. Thermal properties and behavior upon heating. Thermoplastic have distinct glass transition temperature and melting temperature, and below TG, they are hard and glassy. Between TG and TM, they become softer and more pliable, and above TM, they melt and can be reshaped. This melting and solidifying can be repeated multiple times, making thermoplastic recyclable. For thermoset and structural feature, thermoset are heavily cross-linking polymer. This cross-linking occurs during a curing process which may involve heat, pressure, or chemical agents. One set, the structure is very rigid and inflexible. Thermal properties and behavior upon heating. They do not have a true melting temperature because their cross-linking structure doesn't allow the polymer chain to flow past each other. They have a glass transition temperature below Tg. They are hard and brittle. Above Tg, they may become slightly more flexible but will not melt. Instead, they will decompose or charred or exposed. For elastomer, in structural features, their lightly cross-linked structure allow them to stretch and then return to their original shape. It prevents the polymer chain from sliding past each other completely, which give the materials their elastic properties. For thermal properties and behavior upon heating, elastomer have a low Tg, which means remain flexible and elastic over a wide temperature range below their degradation temperature, and they do not have distinct melting temperature because because they cross-linking prevent the chain from moving freely enough to enter a liquid state. And upon heating, elastomers soften but do not they degrade before melting. For the impact of molecular weight and PDI on thermal properties, for molecular weight, higher molecular weight increase in Tg. This because larger polymer have more entanglement and higher degree of chain interaction, which restrict the mobility of the chain, require more energy and higher temperature to reach glass transition. So for lower molecular weight, polymer with lower molecular weight typically have lower Tg value, as the shorter chain have fewer entanglement and can achieve the necessary of mobility for the glass transition at lower temperature. For melting temperature, a higher molecular weight. For semicrystalline polymer, a higher molecular weight can lead to higher Tm. Longer chain can pack more efficiently into the crystalline structure, which stabilize the crystals and require more thermal energy to melt. For lower molecular weight, a lower molecular weight may result lower Tm due to less efficient packing and weaker intermolecular force in the crystal region. For polydiversity index or PDI, narrow molecular weight distribution, you can see in the graph. Narrow distribution indicate that the polymer chain are more uniform in size. This uniformity can lead to more consistent, predictable thermal properties. For example, a narrow PDA can contribute a sharp TM peak as most of the polymer chain will melt at similar temperature. On a narrow molecular weight distribution also influence the Tg to be more distinct, as uniformity can in chain length result in similar mobility contained across the materials. For broad molecular weight distribution in PDA, a broad distribution means there is a wide range of molecular weight within the polymer's temple. This can lead to broader melting range as different chain length with a melt at temperatures. So the TG might also be less distinct or broadened as various chain length will transition to the rubbery state at different temperature due to the variation in chain mobility. So overall, the effect on thermal behavior and stability is first, high molecular weight and narrow PDI. Such polymer would typically have a high Tg and Tm and exhibit a narrow transition range for both, reflecting a more thermally stable material with sharp transition points. For high molecular weight and broad PDI, these polymer may still have high TGNDM, but the transition will be broadened. They might have increased toughness due to the presence of both high and low molecular weight fraction. And third, low molecular weight and narrow PDI. These polymer will have lower TGNTM and display sharp transition points. They may be less thermally stable, but could be more processable due to the lower temperature required for shaping. And for low molecular weight and board (PDI), such polymer will have Bohr's range of thermal transition temperature, which can result in material with less predictable behavior. Next question, role of crystallinity in determining thermal properties. So first, what is crystallinity? Crystallinity refers to the degree of which a polymer resembles a perfect crystal. In polymer, this can be very form fully amorphous or nor crystallinity to fully crystalline, 100% crystalline, with many materials falling somewhere in between. Crystalline region are well ordered and packed closely together, while amorphous region are more randomly arranged. For effect on glass transition temperature or TG, for starting to amorphous polymer, the TG is the temperature at which amorphous polymer transition from brittle, glassy material to soft rubbery one. For crystalline polymer, as the level of crystalline increase, the Tg of the polymer tends to increase. This is because the crystalline region restricted to the movement of the polymer chain, requiring a higher temperature to achieve the mobility associated with the glass transition. For effect on melting temperature or TM, amorphous polymer do not have well-defined melting temperature as they do not have crystalline structure. For crystalline polymer, an increase in crystallinity usually result in increase in melting temperature. This is because the strongest more order molecular bond in crystalline area require more energy or higher temperature to break. For overall thermal stability, increased crystallinity, generally polymer with higher crystallinity have greater thermal stability, the order regions less susceptible to thermal motion and degradation than their amorphous counterparts. For the implication, this increased thermal stability makes highly crystalline polymer suitable for high temperature application. The implication for mechanical properties at low temperature, below the TG, polymer are typically hard and brittle, and increased crystalline can lead to increased rigidity and strength due to the well-ordered molecular structure. At temperature between TG and TM, in this range, the amorphous region of semicrystalline polymer become more mobile, leading to increased toughness. The crystalline region contribute to provide structural support, and above the melting temperature, the mechanical strength of crystalline polymer decrease sharply as the crystalline structure break down. So that's all for me. Thank you so much for your attention. Have a nice day.